Going to discuss about amplitude modulation. Comes under first unit. The course outcome of first unit is distinguish various amplitude modulation communication systems. So what is the definition of amplitude modulation? Yes, it is a process of changing the amplitude of high frequency carrier signal in accordance with the instantaneous value of modulating signal. What are the applications? Applications of AM is two-way mobile radio and audio and video broadcasting. So now we are going to derive the AM derivation. So modulating signal is represented as EM sin omega MT. Carrier signal is represented as EC sin omega CT. So according to the definition, AM is the amplitude of the carrier signal is changed after modulation. So we can represent EAM as a instantaneous magnitude of modulated waveform after modulation. It is a combination of maximum magnitude of carrier signal. It is going to be modified according to the input signal EAM of t. So substitute this in the above equation. So we will get EC plus EM sin omega MT. So EAM is equal to EC into 1 plus MA sin omega MT. Please remember this equation. This is the basic equation for deriving the AM equation. So what is MA? MA is the modulation index, ratio of maximum amplitude of message signal to the maximum amplitude of the carrier signal, simply EM by EC. Percentage modulation is indicated as capital M. Capital M is equal to EM by EC into 100. So in other words, we can write the percentage modulation as modulation index into 100. It is otherwise called as 10% modulation. So the relationship between modulation index, maximum magnitude of modulating signal, carrier signal is represented in this waveform. So this peak to peak value is considered as the E max and E minimum value. This is E minimum value and this is E maximum value. So this is going to be the EM, that is the maximum magnitude of modulating signal. This portion is also EM. So by relating all these things, we can write modulation index is equivalent to E max minus E minimum divided by E max plus E minimum into 100. So the instantaneous amplitude of modulating signal at any time can be represented as EAM of t. With respect to the time period, we are writing the amplitude modulated waveform as EAM sin omega CT. So EAM of t is equal to, already we got EAM, substitute that value. So EC into 1 plus MA sin omega MT into sin omega CT. Then expand this equation. So if we expand this equation, we will get sin A sin B term. So this is nothing but sin A sin B. So expanding sin A sin B, we will get cos A minus B minus cos A plus B divided by 2. So EAM of t is equal to EC into EM sin omega MCT MA EC by 2 into cos MC minus MM into T minus MA EC by 2 cos MC plus MM into T. So the first term which represents the carrier signal, second term is upper sideband, third term is lower sideband. So the frequency spectrum and bandwidth of AM wave can be derived from the above AM equation. So we will draw the curve with respect to frequency and magnitude of modulated waveform. So this represents the carrier signal. We will take it as a reference, and this is your upper sideband, this is your lower sideband. So this frequency is FC, upper sideband frequency is FC plus F max, lower sideband frequency is FC minus F max. So I told you in the earlier class, bandwidth is defined as the frequency between upper cutoff frequency minus lower cutoff frequency. So here FC plus F max minus of FC minus F max, which gives you 2 FM. Bandwidth of AM can be equivalent to highest upper side frequency and lowest side frequency. So we will get bandwidth as 2 into F max. So this is your AM waveform. So high frequency carrier signal, this is your modulating signal, and the third one is your AM modulated waveform. The shape of modulated waveform is known as AM1. This represents the modulating signal's envelope. So this is called as AM envelope. Phasor representation of AM. So carrier, as I told, this is the reference carrier, act as a reference phase. So this is EC, and this is your modulated waveform VAM of t. This have two phases with respect to the upper sideband frequency and lower sideband frequency. So upper sideband frequency phase will rotate in the anti-clockwise direction towards the carrier. Similarly, this will rotate in the clockwise direction with respect to carrier. So we will get minus omega m in the lower sideband and plus omega m in your upper sideband. So this is the phasor representation of amplitude modulated waveform. Based on the modulation index, modulation can be either critical modulation, over modulation, or under modulation. So these are all under the category of modulation. When EM is equal to EC, modulation goes to 10%. This situation is called as critical modulation. That is, the maximum magnitude of carrier as well as the modulating signal both are going to be same. That is called as critical modulation. So this is a waveform which represents the critical modulation. Both the magnitudes are same, carrier as well as magnitude of modulating signal. Then EM is less than EC, which leads to under modulation. That is, the magnitude of carrier signal is comparatively high than modulating signal. So this is a waveform representation. Then EM is greater than EC, that is, it leads to over modulation. Modulating signal, that is, the input signal's magnitude is maximum compared to carrier signal. So in that case, most of the information lies in the zero axis is cut down. So this is called as over modulation. So for better transmission, we have to prefer EM is less than EC or critical modulation EM is equal to EC. So next we will move to the next topic, AM power distribution. So the power distribution can be obtained from lower sideband, upper sideband and carrier waveform. So generally the instantaneous power of any modulated waveform can be written as PT. Here it depends upon three terms: carrier wave, lower sideband and upper sideband. So PT is equal to PC plus PUSB plus PLSB. So we can write the carrier power as EC square by R. So EC is the maximum magnitude. We have to obtain the average value of the power. So this is equivalent to AC divided by root 2. That is, the root mean square value of magnitude is considered for finding the carrier power. So this is equivalent to EC square by 2R. Similarly, we can find it for lower and upper sideband power also. So PUSB and PLSB are equivalent to, what is the magnitude of lower sideband and upper sideband? So from this equation we can say that MA VC by 2. So the maximum magnitude of lower sideband and upper sideband is considered as MA EC divided by 2. Then we have to find out the average value. So divided by root 2. So MA EC by 2 divided by root 2 the whole square divided by R. So we can find out our USB and LSB both are same because we are considering only the magnitude alone. So MA square EC square divided by 8R is the maximum power of upper sideband and lower sideband. So if we simplify this, your upper sideband and lower sideband in terms of carrier power is equivalent to EC square by 2R. So if we simplify this leads to MA square PC by 4. So either USB and LSB power is equivalent to MA square EC square by 8R, or in terms of carrier power we can write MA square PC divided by 4.